be on here. So the voltage starts out as the full voltage of the battery. But what happens is, eventually, the current is going to drop. See, because the voltage resistance is a constant. So what's changing here is the current through the circuit. Why is the current going down? Well, it's because this is an open circuit. So in the long term, the current must stop. It's like if I had a battery, a resistor, and an open circuit. The current may flow instantly to go this far, but then finally, in the long term, it's got to stop because it's open. Can't get across. So the current will go down. What I didn't want you to have to be fussed with is the actual e to the minus t over RC is the way this thing goes. It's exponential, and we're not too familiar with that. Okay, that I don't want you to bother with. But I want you to know the general idea that over a period of time, it's pretty obvious, fundamentally, that this is going to go down to zero in long enough time. In a time, as I said, well, this so-called tau time constant, in a time roughly r times c, it will fall about to there. Okay, so what happens then is the current comes over, the charge builds up on this capacitor until you reach the situation where the capacitor has as much voltage on it as this EMF that's pushing the charge through. At which point, all the voltage is across the capacitor, and it just stops the flow because there's no potential difference. You see, the voltage here is as strong as here. The potential difference between here and here is zero. Potential across the resistor is zero. And by the law here, the current is zero, and the voltage drop across the resistor is zero. So that's the long-term behavior of the voltage across the resistor. The amount, then therefore, this thing, the voltage on the capacitor, let me make it colorful. The voltage on the capacitor starts out at the EMF. This one starts out at the EMF of the battery. This one rises up to the EMF of the battery. Do you see that? After a long time, charge has moved over. The voltage has built up to the point where it's equal here as here. So there's no more current flowing through here because there's no potential difference here. So the current stops. And at that point, the voltage on the capacitor is the full voltage of the battery. And there's no voltage on the resistor. There's no current on the resistor. There's no charge on the resistor either because resistors don't hold charge. All there is that this, in the final picture, let me maybe put it over here, the final picture will look like, if you have your battery, you'll have the resistor, you'll have the capacitor, and this will be charged up with a certain amount of charge Q on the plates. Q will be equal to C times the V. So whatever capacitor was here, a certain amount of charge will be on this capacitor, depending on its C. And the current will be zero, because this voltage here will be equal to the voltage of the battery. So that'll be the final state, if you wait a few RC times. Is that there? Yes. Tau represents the time to fall about 2/3 of the way. It's measured by RC, in seconds. You just pick a product of RC, will give you an approximate characteristic time. I mean, officially it'll take forever, but 2/3 is close enough for government work. Yes, is there a question? Okay, so that's the point. Now, the other thing, so you have a current flow for a while. The current eventually will stop. And that's that. Then if you open the circuit again, let's see how you might do that. Well, for example, okay, so you have a charged up capacitor like that. So this guy's all charged up here. We got plus Q and minus Q on the plates. The magnitude, the total charge is zero on the plates, of course, plus Q and minus Q. But the sum, but on each plate there's a plus, and the other plate has a minus. Sum total being zero. Now, if I put, say, short circuit here, and I close this, so I take out the battery, which is maintaining the balance here. What will happen is the plus charges now, they have a path unopposed to come through opposed by the resistor. They will flow through the circuit, and the plus charges will flow to the minus and cancel out. Also in this time, RC. So what you'll get in this case is, if you were to plot the voltage on the capacitor versus time, this is now the discharge stage. You started out, it had the full electromotive force of the battery to start with, but it's going to drop like that, give up its charge, and because it's Q over C, as the charge goes down, the voltage will go down, just run around and cancel out. And what's going to happen here, current will flow. Because the current charge is moving, I'll have a current, which is the amount of charge that was on the battery over the time it takes to go across, which will be roughly RC, actually. Or some other time that you could, for example, dial in the time here. You could maybe slowly make this connection and adjust the time. So that might be the time you put into this, how much time it takes for the charge to get across. In which case, what am I plotting here? The voltage on the resistor, it will start off, this is interesting. As soon as I let the current go, current is going to be high. So the voltage on the resistor will be pretty high, but there's still charge on the capacitor, and the whole thing has to add up to the voltage here. So it'll probably do something like this. Let's see. No. It's probably going to do, let's see. The total voltage is going to be the voltage here. So this is going to be zero. The current will go up, and then the current will, in fact, go down, won't it? I haven't really thought about that too much, but there you go. It's got to do something like that, right? Because eventually the current's got to go to zero. So I think the voltage on the resistor will go up and down, and the voltage on the capacitor will, the sum of these two have to, no, they don't have to add up anything, actually. They don't have to add up anything because there's nothing forcing it to be anything. So I would think you're going to get something like this. The voltage on the resistor is going to go, you see why? At first, you always have to have Kirchhoff's law, that the voltage on this plus the voltage on this adds up to zero. So when the current comes out, you're going to get a voltage drop across this resistor as the current flows. This is getting to be a complicated problem, actually, now, because the charge is coming off of this, but there's only a certain amount of charge. See, there's only a certain amount of charge, and it's got to get off in a certain time. It will get off in a certain time, and then it will disappear. There'll be no more charge. So the current has to go up and down in some interval of time. So this actually is a measure of the current that's flowing over a period of time. And you will get kind of an average current over this time, which is sort of the total charge that transfers over the time it takes. It's actually a good question. Sort of see what I'm getting at here? That when you discharge it, there's a certain amount of charge trying to get through the resistor to the other side. It will take a certain amount of time, and if you know that time interval and the amount of charge, you will then get the current that flows. Say it a little louder, can you? Hear me? The current will flow, this is now a charged up thing, the current will flow this way, right? And it will cause a potential drop, of course, here. So if you add up the potential drops, you're going minus to plus, plus to minus, and the whole thing around the circuit should give you 0 by Kirchhoff's law. So we agree on that? Good question. I think the answer would be, here's my circuit. I have a resistor, and I have my capacitor, and I put a short circuit here. I start out with this, plus and minus, and clearly the current is want to run through here. When it goes through the resistor, it drops like that. Do we agree? Okay, so if you add up the voltage drop around the loop by this Kirchhoff law, you go minus to plus, so that would be an increase V, plus a V, plus a V. Then you go from plus to minus, which means a drop, so it's minus IR. And Kirchhoff law would say if you add all of those, they have to come to 0, because I'm back to this place. Right, so that the voltage, right. So if you really want to do this right, what you have to put in for V, you have to put in Q over C. And Q is varying in time. And so what you end up with, I am sorry to say, is Q over C minus IR equals 0. But I is dQ dt. So you're ending up here. This is what I'm trying to avoid. You try to solve this, it's a differential equation of sorts. You get dq over q equals dt over rc. For those mathematically inclined, you then integrate both sides here, and here's where you get your rc time constant. So what's literally happening here, the charge that was accumulated there transfers over, and it sort of is used up. And so you get this decline in the voltage on the capacitor because it's losing its charge through the resistor. And the resistor, the voltage is high, but then eventually the current goes down. How could that? At t equals 0, let's see. At t equals 0, the voltage on the capacitor is certainly the original voltage. So there must be no voltage on the resistor. But then current starts to flow, but in the long term it's got to go to 0 because the current, the charge is all used up. Yes, sir? That's right. Ah, yes, that's true. Ah, that's what you're trying to say. Ah, you're right. That's great. You guys are terrific. Oh, save me here. Thank you. Oh, that's really good. Very good. Okay, yeah, let's do that. Bravo, 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 bravo. Very great. Okay, let me leave that because we want to talk about this other whole set of issues. Thank you very much. That's great. Straighten me out. That's very good. Okay, looks like I'm not going to get an A in this course. All right, try again next time. This one, it comes in various pieces. Okay, the one piece, somebody asked about graphs. Okay, if I have a negative ring here, it's producing a negative electric field. Okay, so, and clearly, if you plot the electric field, it's going to be, from a great distance, it's going to look like a point charge, right? So it's going to be negative, and it's going to go as proportional to 1 over r squared, that way out here. And this charge on the ring is going to, in fact, be over here, and you'll have your 4 pi epsilon naught, or we can represent that by kq over r squared. Okay, then we can ask what is the electric field at the center, and there we said, in this case, because it's symmetrical, the electric field of these negative charges here, I think I put negative charges here, you'll have lines going toward the negative charges, but they will cancel out, so you'll get E at the center is 0. So at this point x equals 0, it's 0. And so we get the idea that it must pass through a minimum someplace, which we'll guess is roughly the radius of this thing, because that's the characteristic length of the problem. So that would be E. If you want to plot the force is equal to the charge that's moving, which is this electron coming in here, is E, right? So it's a negative charge times a negative field. It's going to make the force look something like this. Way out here, the force is going to be K, Q on the ring times the electric charge here, but because they're both negative, the whole thing will be positive, and the force will look like that way out there, and it's going to pass through a peak and go to 0 over here. In fact, it's going to go negative. By continuity, it's going to go negative over here. This will go positive over here. So the force will actually reverse direction. The force was pushing the charge away as it approached the negative thing. When it passes through, if it should pass through, it was negative, and it sees this negative thing here, which will push it away. So that's why the force sort of reverses sign. It becomes a force in the negative direction. So it's a negative going force, which means it's pushing in the minus x direction. And if you plot the potential, you can plot the potential and the potential energy. The potential just keeps going. Now the potential has a sign to it. It's negative, and it reaches a value in the middle. and then it goes, in other words, that's the potential V. The potential energy has, because you're multiplying V times a negative charge, V is negative, E is negative, the potential energy will go up, which is reasonable. In other words, a negative charge going toward a negative thing, it climbs the potential hill. The trick to get the answer to the question is that what you want is that the potential energy at x equals 0, this will be U at x equals 0, has to equal the kinetic energy that you start with. Right? And then the particle will ride up the hill with its kinetic energy. It'll convert all of its kinetic energy exactly into enough potential energy to be at the top of the hill and stop. And then it will stop because it just rode up the hill, just enough to bounce on top of the hill, and it stops because all its kinetic energy is going to potential. And so the solution to the problem is that somehow you have to find which I think we were able to do in this case, the potential energy at 0 from some way or other. Actually, it's not too hard. Oh, we have this whole problem here. Basically, it's Q. It's Q. See, the total charge around here is Q, and they're all a distance A away. So you have K, Q over A. I think we'll give the answer. For the that's the potential, and then you multiply that by the charge E. That's the potential at that point. So the charge has come in, it's ridden up the potential hill, it stops there, and then it's equal to half mv squared. So will be K, I believe this will be right, over A times E. And then I just solve for V, which is 2KQE over A, and I divide by M. And then I take the square root. And that's the answer, I think, unless I got the potential wrong. So the idea is that you're using the fact that the kinetic energy that you start with plus its potential energy at infinity, which is 0, will be equal to the potential energy at the end plus the kinetic energy at the end. And that is going to be 0 because you say it stopped. So we've just said that the U final then is equal to the kinetic energy. That's quick. Now, personally, I can stay if anybody wants to stay. And unless we get chased out of here, we can stay here. Or else we can go back up to my office. Is that good enough on this? The other thing I'd recommend to you was get some rest before the exam, eat something, bring an eraser, unless you're perfect. And, oh, by the way, just the exam is, maybe seem rather long, but it is made up of small pieces, sort of like this. If you get each, don't worry about so much the grand problem, perhaps. Look at each piece. I think you'll find that if you build up and solve each little piece, you'll get the whole thing. So don't be intimidated. It's probably easier. I hope it's easier than it looks. I will work on this one, though, for those who want to see it.